The key to this lesson is to understand what is an unfortunate reality, that there's many ways to evaluate this integral, or integrals in general. One way is actually the last way we're going to talk about, which is using your calculator. What we're going to talk about, though, is what your calculator does in the background. So we're going to start with this behind the scenes as like the first half of the lesson. The remainder of the lesson will be the other two ways, which is what? What's like one way besides plugging this into your calculator that you could get the answer? Say, if you don't have a calculator, how would you evaluate this integral? Just to remind you, when you were first introduced to this notation of an integral, it meant something other than accumulate. And if I didn't have this -2 and this 2 here, this does not mean accumulate. What does that symbol of an integral mean without those numbers? Antiderivative. So for hundreds and hundreds of years, human beings had to take antiderivatives to find accumulation, which is why your calculator's accumulation button looks like an antiderivative, because it is. It's an integral. It just means a lot. Now, when you take the antiderivative, you understand that you have this plus c, but we realize we don't need it. We just need the antiderivative at 2 minus the antiderivative of -2. We find the displacement of our antiderivative. Remember, when we were introduced to this first concept, we had a velocity that was positive. It told us our position was increasing. When we accumulated our velocity, it told us how much we increased. We could find a position at a start and a position at an end, subtract them to get that value. It was like the whole triangle, how x of 0 plus this is x of 2, x of 2 minus this is x of 0, x of 2 minus x of 0 is that. So that's calculus. You take the antiderivative, you may have a plus c, but when you subtract them, it goes away. Now, we have not been doing this, but we're going to start doing it a little bit more now. You could take the antiderivative, cross off the c, knowing it doesn't matter, and put a line next to it. And this line says, hey, I've taken the antiderivative. Don't forget to plug in 2 and -2 and subtract them to find the change. So that line kind of means change. You plug in 2, you plug in -2, you end up with the answer 32/3. Cool? You found big F, or you found really what just is the antiderivative of what's given to you. You plug in 2, you plug in -2. The other way, which sometimes is available to us, is to use geometry. Now, if you have straight lines, you win. You can just find the area under your straight lines using geometry. But if you have curves, the best you could do is use a Riemann sum to approximate. Curve. Okay, so that's the unfortunate thing, is that, man, I could have 3 different ways to find one thing. Students would prefer one, because then, that's the most helpful. Now, obviously, we love the calculator method because it's the quickest. If we had a calculator, boom, 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 bang. But what we need to start with is actually the behind-the-scenes look at what does your calculator actually do. It involves our understanding of Riemann sums, and it's going to be funky looking. In the end, it's not a big deal, but it's something you're required to know. Many of you will forget it, and it's not the worst thing in the world. But let's just see if we can conceptually understand where it comes from. So when we use the Riemann sum, what were we doing and what were we using? Can you just tell your neighbors, try to remind yourself, like, what is a Riemann sum? What did we do? What did we usually use when finding a Riemann sum? Go. Very good. Many of you on top of things. If you're not, it's okay. It's been a week. We took a sum of areas. Now, here comes the first half of the lesson, the behind-the-scenes approach to what a calculator does. When you plug this into your calculator, it actually doesn't take an antiderivative. It instead uses an advanced Riemann sum. It takes the sum of areas. Now, what objects do we use for 3 out of the 4 Riemann sums? Rectangle. Now, space this out. Let's come over here. Here is the behind the scenes. What does your calculator do? Okay, we can take a sum of areas of rectangle. Now, what is the formula of an area of a rectangle? Tell your neighbors, what do you get? A base times the height. I'm going to say it's a height times the base. Now, with our Riemann sums, and again, this is what your calculator does and behind the scenes, is it uses a Riemann sum. Where do the heights come from and where do the bases come from? Well, let's say it's a right Riemann sum. Where do the heights come from? Where do the bases come from? Tell your neighbors, where are the heights? What are the bases when we were doing Riemann sum? Good. We had y's, specific y's on the right if we were doing a right Riemann sum, and we had some x lengths. We call them delta x's. Great. All right. Well, I'm going to just show you an example of what could be typed into a calculator, which is the behind-the-scenes approach to what your calculator does. The y's come from plugging in x's into an equation. So I'm going to change that to that. Okay, now I want you to answer this question. How do we know what our base lengths are? How do we know what our delta x's are? I want you to answer this broadly, not like specifically. Tell your neighbors. How do you know what the base lengths are? Sure. Many of you are like, well, it's just like 1. Well, sure, that's one example of what your delta x could be. What if I wanted to use like 8 objects? What would be my delta x in that case? If I use 8 objects, let's say I use 8 rectangles, Billy. If I use 8 rectangles, what is the width of every rectangle? Between -2 and 2. 0.5, right. Hopefully you are saying this depends. It depends on how long your interval is and how many objects you use. There's a very simple formula for this. We have an overall interval length divided by an amount of objects. How do you find the length of an interval overall? -2 to 2, you guys know it's 4. But what if I went from -1 to 2? you know that it's 3. What do I do to the numbers -1 and 2? What is the operation done to them to get the answer 3? No, not the absolute value. How can I turn the numbers -1 and 2 into the answer of 3? The length is 3. 2 minus -1, subtracting. So here's your first thing. Delta x is by taking your overall interval length and dividing it into an amount of objects. We're going to say the amount of objects is n. Okay. Now here comes the tricky part. Where did we get our y's? Well, we got them from a function. But we had to plug in specific x's. We are going to denote these x's. If you have space, you need it, as x sub I. We're going to say specific x's times our delta x. And we want the first x, the second x, the third x, the fourth x, all the way to the nth x. So we want n total objects, which means we need n total x's. We're going to say, and this comes from summation notation and what it means. You take the BC calculus test, you need to be more comfortable with summation notation. This means start with 1, meaning it's x sub 1, it's the first x, go till n and stop there, which means you will have an n amount of x's being used. It's integers starting at 1. Okay. But the integers we use need to start at A. What is A? The A is the starting point. You know, this is all from A to B. A is the starting point, B is the ending point. That's what B minus A comes from. A is the starting point. I got to start at -2. And then I need to move over like a little X length. Get my first X, boom, plug that in. And then I need to move over a little bit more to get my second X, plug that in. And I need to move over a little bit more, get my third X, plug that in. I need multiples of delta X added to A. That becomes I delta X. I is the integer starting at 1. You have A plus I delta X, boom, that's it. Again, this is just height times width. But from this formula, and this is the thing that you need to write down, this is the behind the scenes look at what your actual calculator does. It's not a big, huge, important thing for this overall lesson, but it's something you need to know. You are able to produce a calculator behind the scenes formula to get an integral. I will take f of x, which is 4 minus x squared, and I will do 4 minus x squared. These are my heights, times delta x. I will replace b and a with 2 and -2. I know the overall length is 4. I get 4 over n, for b minus a over n. This is the length of each subinterval. I will replace a plus I delta x with -2 plus I times 4 over n. This is actually what goes on, something similar to this, behind the scenes when you plug an integral into a calculator. I'm going to show you it with Desmos really quick. You type in an integral, your calculator does not use an antiderivative to get this answer. Instead, it does something similar to the following. It takes a sum, I starting at 1, going to n, of using what you type in, as well as a and b, it'll convert it into a sum. We'll do 4 minus a plus I times delta x squared times delta x. Okay. This is what my calculator got. This is what we got by taking an antiderivative. I will be able to change the amount of objects we're using just by typing in a different value. If I use 2 objects, I get this sum as 8. If I use 4 rectangles, I get 10. If I use 8, I get 10 and a half. If I use 100, I get 10.6656, 1,000, 10,000, 100,000. As I use more and more objects, my approximation gets more and more accurate until it just says, there's your answer. Now notice it takes me 1 million rectangles to get the same answer that they got pretty quickly. What your calculator actually does is a more advanced Riemann sum. It uses trapezoids sometimes, uses midpoints and trapezoids. It does a better numerical process than just using a right Riemann sum. But this is the idea behind the scenes with your calculator. Your calculator does a sum. The more and more rectangles you use, the better and better your approximation is. You are responsible with being able to create this, to be able to create a right Riemann sum fish behind the scenes look. I would like you to try that with this example on the bottom. I'll give you a hint. You just need to plug in the right stuff into this formula. So give it a shot. Don't say I don't know how to do it. It's really not that bad. You just have to plug in the correct stuff. This equation is the log x equation. F of x equals log x. Okay, go. Give it a shot. Again, like, it's not that big of a deal in the grand scheme of today's lesson. Today's lesson is really focused on making sure we're comfortable with all of the different ways to find areas, accumulations, whether you're using an antiderivative, using geometry, or, you know, if we're able to plug it into our calculator, great. We could plug it into our calculator. Here's the behind the scenes look on the calculator. I mean, here's the formula. You just got to plug in the right x's as the y's, and then this is just height times width, base times height. And if you never embrace it, it's actually not that big of a deal. It's good if you move on to BC calculus and calculus 2, understanding that. All you got to know is that this is our start, this is our end. So our delta x is 3 over n.
I was confused where to put the 3. It's like for here, like, was that just because this was part of the 4 minus x squared?
Yes, because this is 4 minus x squared.
Okay.
Since this is just log x, it's log of our x. The previous one was 4 minus our x squared. What are you doing with your phone? No, you're not. Put your phone away. What did I say at the beginning of class? No, it shouldn't even be on your table. It's going on YouTube for forever. Me yelling at you for having your phone out. Can you put it away? Can you put it in your backpack? No, I don't trust you.
He took my phone. He literally just handed it to me.
That's funny. Yeah, take it off. Goodness gracious. All right. What time's lunch? 58? All right. Get out of here. All right. So, the behind the scenes calculator, it's something that is not super important. We move on, knowing that you can always plug in an integral into a calculator. The calculator does its work behind the scenes. What you need to remember is, like, there are two ways. Put your phones away. Give me that back. Is the antiderivative way? There is potentially a geometric way. Sometimes you'll be able to do the antiderivative. Sometimes you'll be able to do the geometry. Sometimes you'll be able to do both. You got to pick. Maybe big F of B minus big F of A is something you're going to do. Maybe just finding the area is what you're going to do. Regardless, you'll get a positive answer if your function is above the x-axis. You get a negative answer if your function is below the x-axis. Something we remember. Now, reason why the area can be considered positive or negative is thinking about that we could think about it as like a sum of y's and x's, you know? If you're going from left to right, your x's are positive, your y's are positive. Like, you could think about it this way, but really, if you want to use like a trapezoid to get your answer, you get your answer. Just above the x-axis, positive, below the x-axis, negative. How does that work if we go from right to left? Well, guess what? You're going to be doing big F of A minus big F of B. That's the antiderivative way. You will use geometry. If you think about the behind-the-scenes action, y's times x's, if you go backwards, your x's are going to be negative. Regardless of how you do it, you're going to get your answer is negative or positive. It'll be the opposite of what we think. We understood this from last unit. This is actually the exact same as your notes from last unit, a little bit. Okay? Two options. You can either do F of A minus F of B. Oh, right, that's the same as the opposite of big F of B minus big F of A. We see how that works out. And if you want to think about it geometrically, either you can go back to like your understanding of motion, and if you're going back in time, you're going to do the opposite as going like normal time. You're going to subtract. You have your little triangle of understanding. Great. If not, whatever. You're fine. What was the answer to this one again? Tell your neighbors. A to A, this integral? Yeah, you know the answer is 0. Well, if you think about it using an antiderivative, what's big F of A minus big F of A? Yeah, that's 0. That makes sense. If you think about it using geometry, maybe thinking about the behind-the-scenes work with your bases and your heights, well, your delta x is 0. There's no x system. Okay. Sometimes you will be able to just take an antiderivative, no big deal, and the constant in front of the function isn't going to change anything. For example, if I have the integral of 3x squared from 0 to 2, this 3 is not going to change anything. You would just take the antiderivative of 3x squared. Everybody take the antiderivative of 3x squared. Wake up! Yeah, okay, get the answer. What's the area under 3x squared from 0 to 2? Great. I love how both of you are thinking. And you're like, 8. Yeah, so you take the antiderivative, you plug in 0 and you plug in 2, you get 8. So like, no big deal, this 3 is going to affect it. But if you do the geometric way, it might be beneficial to use the following property and pull out the k. You're allowed to pull out the k. Constant times an integral isn't going to change anything. If you pulled this 3 out, you'd have 3 times 1/3 x cubed. The constant doesn't do anything. So if this area is 2 and you have 3 times f of x, this area would be 6. It's very easy to figure that out. Just take that 2 multiplied by 3. Cool? The k does not affect the antiderivative. Now, it's easy to kind of think about this geometrically, which can then lead us to a better antiderivative approach. This is something that's new, but I bet you can figure it out. If you have an integral from a to b plus an integral from b to c, what is that equivalent to? Tell your neighbors. Wake up. Try it out. Yeah, guess what? Instead of doing these separately, you can combine them into one integral, and then all of a sudden, it's a lot easier to take the antiderivative and plug in c and take the antiderivative and plug in a versus b minus a plus c minus b. Oh, yeah, the b's are going to cancel if you want to think about it that way. F of b minus f of a plus f of c minus big F of b. Oh, the f of b's cancel. You end up with f of c minus f of a. Oh, like, boom. Does that make sense with the antiderivative method? It's like, it's weird to see it, but it works out. And it's just that. Okay? Regardless, just showing you sometimes better to combine things, maybe using your geometric idea of the area, and then you're good to take antiderivatives and go from there. Now, let's say I had an integral from 0 to 2 of x plus x squared. It is easy to take the antiderivative of both of these separately. And then plug in 0, plug in 2. Fine. You could just take the antiderivative of f and the antiderivative of g, and then plug in b and a, and that's fine. However, if you are going through a different approach, a geometric approach, depending on what you're given, it might be more beneficial to split them up. Cool? You will see an example of us using that in a second. Where like one method isn't going to be easy, the other method should make sense, but you're going to get the wrong answer, but then you'll split it up and get the right answer. I'll show you what that is. Here, let's just change this exactly to a number. What if we are trying to accumulate from 1 to 5 the constant 3? What would be the 2 ways to get the answer? What are the answer 2 different ways? Like, what's the answer? How do you get that answer 2 different ways? Go. Get the answer 2 different ways. The answer is 12. Get it 2 different ways. This is the beginning of this lesson, really. Getting the same answer 2 different ways, being prepared to use the antiderivative, being prepared to use geometry. Certain situations are helpful. Certain situations you can only do one, not the other. Here's a situation you can use both. There are 2 different ways to get the answer 12. What are the 2 different ways? What have I been talking about over and over again? Go. You should be trying the antiderivative approach. You should be trying the geometric approach. You can do the geometric approach in this situation because this is a straight line. Straight lines, you can use geometry. Guys, this is the key to the lesson. This is the key to the rest of the year. This is the key to the AP exam. Like, sometimes you have to do it one way versus another way that you prefer to do it. Sometimes you will have to take antiderivatives. Here, I'm going to use this notation of a line to show I'm finding the change in my antiderivative. Plug in 5, plug in 1. You get 15 minus 3, the c will go away. You get 12, the antiderivative approach by doing 15 minus 3. Versus the geometric approach, since it is a straight line, we can use geometry. We have a height of 3, a width of 4. You get 12. 2 different ways. Cool? Depending on the situation, you need to be able to either do one or the other. Think about doing it both ways. For example, let's say I'm asking you this question. What is the integral of f of x plus 3? Cool, I'm giving you that. Let's say I tell you that the integral from 1 to 3 of f, which you could find, is 3. This area is 3. Find the answer. Well, you could attempt to take the antiderivative, big F of x plus 3x plus c, and plug in 1 and 3. But the problem is you don't know what big F is, so that doesn't really help you. You might be saying, oh, the answer's 6. Yeah, you're wrong. It's not 6. Okay, so see if you can find the answer. Maybe take the geometric approach, which says it might be beneficial to split this up into multiple integrals, and then realize, oh, the accumulation of 3 is not going to be just 3. There are 2 ways to get the accumulation of 3, whether it's the geometric way or the antiderivative way. And get the answer. What's the answer? The answer is 9. This was already found geometrically. This can be found multiple ways, either taking the antiderivative or using geometry to get 6. This is 3. This is 6. The answer is 9. Okay? Flip the page. Don't write another. Switch this with 2 ways for this. 2 ways to do this. Change that to 0. Whatever. Who cares? If it's 1, it's fine. 2x is just a straight line. This is a straight line. If you know it's a straight line, you know you're going to be creating a triangle. Base 3, height 6, this area is 3. That's, you're done. Is that right? No, that's area is 9. I'm not a geometry teacher. Maybe one day. One of my favorite college math classes was college geometry. It was hard. But what The other way to get the answer 9. Please get the answer 9 the other way. Great. The antiderivative is x squared plus c from 0 to 3. You plug in 3, you get 9. You plug in 0, you get 0. Okay, I get that same answer 9. Do you have two ways to find this answer? Over here on the right. Not a straight line. You can't use geometry. You have to take the antiderivative, plug in 2, plug in 0, subtract, get the answers. Okay? Being prepared to do either way depending on the situation. Being prepared to use geometry's ideas to get us answers. Understanding sometimes it's beneficial to split things up. For example, look at this one on the right. Go to the one on the right. We're just going to do a couple of these, and then we're going to get to the homework problems, okay? We're done early, and you guys just twiddle on your phone. And what is it? Clash? Smash? Brawl Star? You want Brawl Star? You get your Brawl Star on. You need to practice anyway, Shotty. Then that's fine. But let's see. Can you do this? All right, ready. You should always be thinking, hey, could I use the antiderivative? It's like, well, I could for 3x, but big F, I don't really have big F, so I kind of don't want that approach. I actually could evaluate 3x's accumulation or 3's accumulation that way. Instead, since I don't have big F, what I do have is actually accumulations of F already given to me. So maybe I'm going to think about this more geometrically. Maybe I'm going to think about the addition of these two functions as being like the addition of two geometric areas, which you then could split up to not do the wrong thing of saying the answer is 13. That's not right. What is the answer? 25. Everybody, why is the answer 25? If you wanted to take the antiderivative of 3, good. You have that option. You have 3x from 0 to 5. If you want to use geometry and say it's a height of 3, a width of 5, that's great. Turns out you're adding not 3. When you add a number, you don't add that much area. You don't add that much accumulation. You can think about it geometrically. 3 from 0 to 5. Rectangle worth of area needs to be added, which shows when you take the antiderivative and use 3x, or you just know that's 15. You add that to 10, you get 25. Be careful, I might throw some curveballs at you. For example, try this one out. This is a good problem. Let's see if anybody can get it. It's on your notes. 5 to 7 is 3. 0 to 5 is 10. Oh, you guys got different answers? So you got 27 and you got 1. Winner. 1 is the correct answer.
It's true. Wait, I wrote it here.
That's great. Good job. I'm very proud of you. It's 1. Oh, Rod, what are we going to do with you, bud? Cool, there's a lot of different ways to do this. I'll show you the way I do it. I immediately noticed that we're going from 7 to 0, and I know that's backwards. I'm going to do the problem from 0 to 7. I'm going to do the problem from 0 to 7 first, get the answer, take the opposite of it. I feel like I won't make mistakes if I do it this way. I feel like instead of taking antiderivatives, which will give me big F minus 2x, that it's probably going to be beneficial to split it up into 2, where 1 is easy to figure out geometrically. The other one we can figure out more, geometrically as well. Like this, we can take the antiderivative and plug in 7. This, I don't want the antiderivative, but I already kind of have the answer. We got this was 13 minus, whichever way you do it, you'll get 14 or add negative 14, which means from 0 to 7, I should get negative 1, which is from 7 to 0, positive 1, the opposite of the answer from 0 to 7. There are other ways to do it where like you split it up first with 7 to 0, and then you flip each answer. That's fine. Fine. Okay. Many of you will be able to figure this out, so let's just go straight to the last 4 questions. Okay, now, this is very much like your homework, so this is a lead into your homework. I would advise you utilize some time in class to work on your homework. This is how it starts. Here we go. First thing is first. Make sure you understand what you have. This is the graph of F. Whenever you are given a graph, circle it 15 times, being like, this is F, or this is F prime. Just know what you have. If you don't know what you have, you might not use it correctly. Okay. I'm gonna change this up a little bit. Put a 2 in front of that F. Put a 2 in front of that F right there. Put a 2 in front of this F. Right there. Now, see if you can get this answer. This is your first challenge in preparation for your homework. Let me get the answer. Okay, I got the answer. Now, your first approach should be to maybe take the antiderivative. But the antiderivative is not F squared. It's like just the constant 2F of X. Plus 3X, the big F does not help you. This is the graph of F. So the antiderivative is not going to help you here. Good thing to think about always. Instead, it might be beneficial to do what Fish is doing and split it up. Maybe take it one step at a time. Good instinct. Maybe it's better to have this as 2F from 5 to 7, and then 3 from 5 to 7. But then again, like, what do we do with this 2? Well, there's something we could do with this 2. We could just take it out. It's just like 2x cubed or whatever. It doesn't affect the antiderivative. The antiderivative of 2f is 2 big F. This 2 can come out. I could just find the area from 5 to 7, the accumulation from 5 to 7 of F times 2. Then You got 5 to 7 of 3. Your answer should be 2. Let's see if you can get 2. Five to 7. 5 to 7.
When we're doing it like on that platform view, and like we're doing this, like if they see that, do we have to like specify that's the anti-derivative or?
Yeah. You have to write down f of x equals to that. Or big F. Yeah, sure. So 0 to 2 is 3. So 0 to 2 is 3. So 2 to 0 is negative 3.
I thought it's 2.5 because we did like split up like that.
Yeah, 1/2 base of 2, item 1.
Yeah.
So you have the right idea, yeah. Okay, so what I do is find the accumulation of f from 5 to 7 is negative 2, because the y's are negative. Multiply it by 2, and this is negative 4. Then, however you want to evaluate this, whether it's using geometry or using an antiderivative, you have both options for this. You get 6. You do not have an antiderivative option. However, f is given to you. It's using straight lines, and you could just find the area geometrically. Now, let's go to this bottom left one, where I say heads up. The top left one is like the first question on your homework. The bottom left one is like the second question on your homework. I asked you for the integral from 1 to 4 of f prime. There are actually 2 ways to do it, but one way is a little bit more complicated than the other one. I'd say one way is a lot more complicated than the other way because you wouldn't be thinking about it. I'd like to see the different ways that you get your answers of a half. How'd you get that? And what'd you think? So you accumulated that half from 0 to 2. But if you accumulate a half from 0 to 2, wouldn't that be 1? Oh, you're going from 1 to 4. So from 1 to 2, you're accumulating a half, which is a half. Good. There's another way to do it, but I like how you got that answer. It is 1/2. There are multiple ways to do this. I think one is a lot easier than another one. 1/2. One way is a lot easier than the other one. I like that, Andrew. I think that's the easier way. Very nice. No, but the only thing is f prime goes to just regular f. You jumped up kind of like one extra step, but you had the right idea. You got it. That's it. I'll show you the other way in a second. Nice. You did. You got it, Cood? Nice. Yeah. We'll probably be going to 5:30. We're learning some tough stuff. Shotty's not going to know what to do with himself, but he's going to figure it out. All right, ready? Here is the easy way to do it. All right. There's actually two ways to do this, but I'd probably prefer you to do it one way. Here's the one way I would want you to do it. Understand that you could use an antiderivative. The antiderivative of f prime is just f. You could find the change in f from 1 to 4. You could find just f of 4 minus f of 1. All of a sudden, this antiderivative method opens up to us. And we can find what f of 4 is. F of 4 is 2, the y-coordinate 2. F of 1 is the y-coordinate 1.5. And we get the answer. There is another way. Though I wouldn't prefer you do it, but it does work. What would f prime look like? Well, if this is the graph of f, the slopes of f are 1/2, then 0. So let's just graph f prime. It's 1/2 from 0 to 2. It is 0 from 2 to 4. If you want to accumulate f prime from 1 to 4, once my cursor comes back, I'll do it. You want to accumulate f prime from 1 to 4, you accumulate this 1/2, this slope, and then you're accumulating nothing more. I wouldn't do that, though. If that's confusing, just do that. Just use an antiderivative. This is the key to the lesson. This is the key to a lot of the AP Calculus exam. Be ready to take antiderivatives. Be ready to find the answer, maybe without using an antiderivative. You're ready to do both. You're ready to use antiderivatives sometimes. You're ready to not use antiderivatives and figuring out the answer either geometrically or using a calculator other times. Okay? And that's it. Work on your homework or clan war. What is it again? What?